where we look at this guy and this guy with two identical antennas and switch the receiver between them quickly and look for a difference. And then the antennas may not be identical, so you rotate it around. So this antenna looks at that side and this one looks at that side. And any change should be the change in the sky, and the equipment shouldn't change. But of course it might change a little if you rotate, so you do a double rotation. So that's the procedures. There's the hardware you have to build, and then the procedures you have to build. And I'm embarrassed to say, looking back, that it took 20 years to do this. But we had to put things higher, and we had to put them in space. But that's what it was. That's what I spent a lot of my life on. So this is one of the first ones we built after we did some on the ground. We built this. So this is a 1 centimeter wavelength pair of antennas that are looking at two different parts of the sky. And this is the ½ centimeter wavelength that, with the switch between it. So why do you do that? Well, the atmosphere is about 400 times as bright at a ½ centimeter as it is at 1 centimeter. So if you see a signal, you can prove it wasn't coming from the atmosphere, it was coming from the sky, because you can look at the ratios. And then you put this in a situation where it can rotate so that you can exchange the antennas. And then you cover it up so that radiation can only come in the horns. You don't want it leaking in some other way. And then you put it in a container, and you put it on an airplane. This is a picture of a U-2 airplane. Most of you guys don't know what this is, but this was a very famous airplane because it used to fly from Turkey to Scandinavia, and would take pictures over the Soviet Union of the installations down below. It would fly very high and very stably and take very good photographs from very high. High so it couldn't be shot down, and very stably so that the images were very sharp. And so after one unfortunately landed in the Soviet Union and was a big disgrace to our president, that was released to be able to do Earth resources. And so all these things in the background are things that look down with optical and infrared sensors to look at the coastline, to look at forest fires, to look at crops, to look at other things like that. And there was one payload which designed to look up at the sky. Everything else is looking down at the ground. And here's a picture of it getting ready to take off, and the graduate student, Mark Ornstein, who got his thesis on it. And here's the fit we made to the data we did with our observation. We saw the sky was 1 part in 1,000 warmer in this direction and varied smoothly to 1 part in 1,000 colder in that direction. So already we're looking at 1/100th of the temperature of the Earth down to the 3 Kelvin, and then we're seeing at 1 part in 1,000 there's a variation, which we call a dipole, 1 warm pole, 1 cold pole. And we think we understand what this is due to. We thought we should understand what it should be due. It should simply due to our motion. If we're on the Earth, we're moving because the Earth is rotating, the Earth is orbiting, and in the direction we're going, it should look warmer because we're running into the photons. In the direction we're leaving, it should look colder. A simple Doppler effect. So you can add up all the velocities that you have on the Earth. So this is where the satellite is orbiting in a polar orbit. But we're flying out of California. The Earth is rotating. The Earth is going around the Sun. And the Sun is going around the Earth. Newton told us all of this. So the solar system is going around the galaxy, and it's going in this direction. I'm going to have to switch lasers. The Sun's going in that direction, but the direction where we're seeing it's going was that direction. That was the surprise. We expected a signal at 1 part in 1,000 because that's roughly our speed around the galaxy, but we're going the wrong way. And that means the whole galaxy is actually moving, right? The galaxy has to be moving almost twice as fast in that direction in order for our velocity to be subtracted to it and still leave us a vector in that direction. So we thought, how could that happen? Well, it could be the local group. We in Andromeda and several smaller galaxies are on a small group. They're orbiting around each other. Maybe that's. But you can measure the speed with which we're coming together, and it's only 80 kilometers per second. That means we're moving the center of mass at 40 kilometers per second. So that can't be the source. So what about the Hydra Centaurus supercluster and the Virgo supercluster? So this is a few thousand galaxies. This is over 10,000 galaxies. Well, that should be enough to pull us over. Well, when you do the numbers, it's not close. And there should be a tidal force that would be stretching the galaxies out. Not just our galaxy, but the group of galaxies we're in. So we had to make up the idea of a great attractor. And then the question came, how are these things distributed in the universe? And I'll show you a picture, I hope, of what that looks like. So we thought we had to go on with our next experiment. So we had to fly higher to get above more of the atmosphere. And we had to cool our receiver with liquid helium and to get it colder so it would have less noise. But we used the same trick. We had the antenna looking at this part of the sky, And then we'd have a mirror rotate in position so that it was looking at that part of the sky. So we're differencing two parts of the sky quickly, and then the whole equipment rotates. And you fly it underneath a balloon with a parachute and with a ladder to rotate against, and you go up and you make observations. So here's our equipment. The same thing, one antenna. Now it's cooled, liquid helium, and then a shield around it. A little thing to flip up so we can see it's working or not working. And then we made this map of the sky, and this is not a fit. This is the actual measurement of each little pixel in the sky. We had 3 balloon flights. We planned for 4, but our payload got lost in the jungles of Brazil, and it was lost for a little over a year. So it was slightly damaged, both by the rain for over a year and by the fact the person who found it tried to cut parts of it off with a machete and sell it in the market. That's how they discovered where it was. But you see it's warmer here by the part in 1,000, going to cooler here by part in 1,000. But you also see the noise of the receiver. But if you estimate how much comes from this signal and how much came from the noise of the receiver and ask how much was there left over, we could say there were no fluctuations at a part in 10,000. And that gets to be a problem because Joe Silk had told us that if we're going to make galaxies after the matter is released, the universe would be 1,000 times smaller. So that if the universe grows by a factor of 1,000, you needed seeds at a part in 1,000 in order for those galaxies to be left behind, and yet we're down to a part in 10,000. So this is beginning to be a crisis. So now the other experiments we're doing, which is to measure the spectrum to see if it's a black body form, they become more important because now we're trying to prove that it didn't come from the Big Bang. Well, we were trying to prove that. So we formed an Italian-American collaboration. We first did observations on White Mountain. So there's a 12-centimeter wavelength from Milano, 6-centimeter from Bologna, 3, 1, and 3 millimeters from Berkeley, and then Haverford College had an atmospheric thing. And then we had a liquid helium door in the ground, so we could look down at liquid helium or up at the sky and have a reference horn that pointed to the North Pole that would allow us to compare different parts of the sky and liquid helium versus the sky. So we went on to do that. That wasn't enough. We decided we'd take our equipment to the South Pole. So this is the Italian-American collaboration at the South Pole. This is the geographic South Pole, not the ceremonial South Pole. We're purists. This is just proof. That's me. Says George Smoot if we had enough resolution. I didn't have a gray beard yet then. That's frozen breath. But you see the horizon's very nice. It's very flat there. And this is, we had to move away from the South Pole where it was quieter. So we had a big ground screen, and we brought liquid helium because the South Pole wasn't cold enough. And then we had a screen against the wind. And we had a pit when the wind was blowing. We could bring our equipment down and work on it, even outside in bad weather. And but at the same time, we were planning the Cosmic Background Explorer experiment. So we have an instrument we're designing to have one antenna looking in the sky and one antenna looking at a 3 Kelvin load whose temperature we could adjust up and down until we saw 0 difference between them. And then we would bring this device in, which is covered up, but it's a simulator of an almost perfect black body that we could then replace the universe with and adjust its temperature to make sure we still had a null and just read off the temperature at each of the wavelengths. And now the results of all those measurements is here, the part that's referred to as the black body form. You see the Penzias and Wilson's original point in red, the point that we measured on White Mountain and the South Pole, shown in green, some balloon flights from the Princeton group, and then an experiment I'll tell you about later on that measured the anisotropy, 3 different frequencies. And then around the peak is the Phi-RAS measurement in red, and you can see how precisely it fits. And then about 6 months later, there was a University of British Columbia rocket experiment that was a small version of the Phi-RAS experiment that confirmed it in a much shorter flight. So you can see the noise. But you have precision over a wavelength range of a factor of 4 decades. Right? So you're essentially going from 70 centimeters to less than 7/10 of a millimeter, right? You're measuring the shape, and the theory, the Big Bang theory, predicts this dotted line. Right? Only the temperature has to be slightly adjusted, but the shape is extremely precisely shown. So now we have the full crisis. This is truly a relic radiation from the Big Bang. This is now late 1989 and 1990. Now we truly have this relic radiation from the Big Bang, and so far the fluctuations we're seeing are below a part in 10,000. And that's a conflict. We can't make galaxies in the Big Bang Theory. There again to be papers appearing in the literature saying the Big Bang Theory is wrong because it can't make galaxies. And there turned out to be two solutions. First of all, we had to get the Cosmic Background Explorer continue taking data. This was the artist concept of what it would be like from the 1970s. There were two experiments inside the liquid helium door. The first one was the spectrum measurement. The second one was designed to look at the first light. That is the light from the first generation of stars and galaxies. And that's called, I'll show you the data. And then there were the experiment that I was responsible for, the differential microwave radiometers. And we were all co-experimenters in all the experiments. So it was a true team effort. Okay, so here's the picture of the whole sky done by the diffuse infrared background experiment. And this was the first very good evidence we have that we live in a spiral galaxy. We're in it. You can see the galactic center and the galactic bulge and the galactic plane. So we're in galactic coordinates. And you see a little fuzzy stuff in here, which is dust and gas clouds in the plane of the galaxy. And you see a few stars off the plane of the galaxy. Though we're in the galaxy, we're almost vertically in the galaxy, but we're far out from the center. So even around us there are stars. So there are a few stars you see no matter which direction you look, roughly. But there's plenty of place to look between the stars. And when you do, you start seeing that there's extra light coming from the universe. And that light is the light that's coming from first generation of stars and galaxies. And if Hoyle is correct, we would think that essentially every time you burn a hydrogen or helium into a element for each nuclei you had, you should get one photon. So just counting the photons should tell us if Hoyle should get his 1% or not, right? And the answer is he should. In fact, when we did the counting, we were getting twice as much as we had predicted. Now, there turned out to be a reason for that, and I'll show you in just a second. But it's because some of the stars started earlier than we had thought, and they were able to burn and make other elements, and that made the dust and the gas clouds you were seeing before. And some of them absorbed the original starlight and re-radiate it in the infrared there, but now the expansion of the universe has shifted into the far infrared. And when it takes a photon and re-radiates it to the lower color, it produces 2 or 3 photons. And so you get 2 or 3 for 1 for sale. So the fact you see twice as many, you have to count the energy and then see that it comes out that is roughly correct, that roughly 1% of the matter in the universe has been burned into heavier elements. So there was another survey since then called the 2-mass survey. And in this picture, it's the first mass picture that I'm showing you. There are over 1/2 billion stars shown. You need a high-resolution screen to see it. Even my screen doesn't quite do it. This is kind of poor. You can see some extragalactic objects, the large and the small magnetic clouds here. But you see the plane of the galaxy. You see the dust in the galaxy and the bulge. And you see many more stars. But you can do the same thing we did before. Instead of blanking out the stars, you can average over the stars here and subtract them from the Derby map, and you still see that roughly factor 2 more photons than we expected, but the right amount of energy that we expected for Hoyle to be right in making the heavier elements in the stars. Okay, so here's a picture of the Cobe Satellite the last time that I saw it. I had to go and inspect it because it launched from the West Coast, and I live on the West Coast of the United States. And you see the doer with a cover over it, because you can't leave it in the air. It would freeze the air around it. And you have to blow the cover in orbit. And then you see the differential microwave radiometers that we had to cool in order to get an extra factor of 2 sensitivity because we were needing that because the limits were getting tighter and tighter from our balloon observations and so forth. And this is a picture of what the satellite looked like in orbit. So it goes into polar orbit, and you try and make it orbit on the Earth, around the Earth on the day-night line, so that the satellite can be looking with the Earth directly below it and the sun at 90 degrees. You tip it slightly back so that everything inside the shield is in the shade. And then you rotate it to keep it uniform like a chicken on a rotisserie. And you have the solar cells, and that way you scan these circles on the sky. The orbit scans those circles around, so you cover half the sky each day, orbit 14 times a day. And then as the Earth moves around the sun, you sweep out a whole picture of the sky, a whole map of the sky. And so here are the maps we made. The first map would be very uniform, so I don't show it to you. The sky is extremely uniform. Here you see the dipole, but now in galactic coordinates. So here's the hottest spot to the coolest spot. Now this is the true data. Now the noise is negligible. You can see what the sky really looks like. And now you also see the galactic plane.